We have two final techniques to talk about. The first one is the profitability index. It measures the bang for the buck, if you will. You take the present value of the inflows and you divide it by the cost. This measure is particularly helpful for firms with capital rationing. Capital rationing is when companies impose a restriction on resources. We need to pick the best uses of our money, and this can give us a picture of that so that we're good stewards for our investors. If we look at the table, again, it shows us the solutions here. We see that the profitability index for A is 1.24. What that means is the net present value of the investment divided by the investment. There's more net present value than cost. If you look at B, we find it's 1.17. Again, as long as the number is greater than 1, the project is acceptable. But again, in this case, has been true these videos, A is a better project than B. The last technique to talk about is something called payback period. There's two versions of this, but the payback period measures how long it takes to recover the initial investment. It's simple and intuitive, but it ignores the time value of money and later cash flows. The discounted version does consider the time value of the cash flows, but it still maintains the other issues of the payback period. An example of this could be very small tech startups that focus on quick payback projects to preserve liquidity. However, larger corporations like Microsoft prefer NPV and IRR since they take a longer term view. And I would also say that in general, all small companies, their projects typically have shorter lifespans. So the payback period might be better for some of these other shorter term kinds of or smaller companies, if you will. So our solutions, again, 2.5 is the payback for A versus 2.76 for B. Again, uh, we need to know what the requirement is for the company. So if our company says we will not accept any projects that have a payback period greater than 3 years, both are acceptable, but again, A is better because it gets its cash flows sooner rather than later. For the discounted payback, the same relationship involves, but maybe we need to adjust that. So, what if we said for the discounted payback period, we need to get our money back in 3.5 years? Well, A is less than 3.5 years, 3.31, but B is greater than 3.5 years. So in that instance, if that was my rule, then we would not accept B. It wouldn't be an acceptable project. Now, one of the things we've talked about a little bit throughout these videos is the idea of cash flows. And in your book refers these as what are referred to as normal cash flows and non-normal cash flows. So normal cash flows involve one outflow followed by inflows. Non-normal flows include multiple sign changes. This becomes very important when we're relying on internal rate of return because it doesn't work with this type of cash flow arrangement. Now, non-normal cash flows do not mean unusual. They happen all the time. Consider a nuclear plant that requires massive upfront costs, decades of inflows, but also later huge costs later to refurbish or to decommission the project itself. These are classic non-normal cash flow projects. So what does this do for our internal rate of return? Well, in this case, if we spend 800,000, then we get 5 million, and then we have to spend 5 million at the end. The cash flow you see here is a negative net present value. I'm not interested in that, but the internal rate of return is 25%, which says that's much higher than 10. But as you look, if we graph this with our net present value profile graph, we see that we actually have two answers. Here's the 25% answer, and that way out here is another one, somewhere like around 410 percent, right? So again, can't have a tool where there's more than one answer. So the modified internal rate of return makes this an acceptable analysis. A couple of, I refer to them sometimes as curveballs, but things that we do have to consider. What happens when we have two similar projects, but they have different lifespans? Many times this happens when two projects are identical, but they have different qualities. One project may be a higher quality, therefore more expensive but less expenses, and also maybe a longer life. And then the other project obviously is what? Has less quality, may ultimately have more expenses down the road, but may have a shorter life. Longer projects will naturally be biased when we talk about net present value because the process of net present value is to sum all the cash flows. So the more cash flows you have, the more you add them up. So we have two projects here, T and F. The net present value for T is 4.132. For project F, it's 6.19. Obviously, F looks better than T, but notice F has a benefit. It has an advantage over T. So there are two techniques that we can use. One is called the annualized net present value. It converts this net present value into an annuitized form for the life of that project. The annual net present value for A is 2.38, and the annualized net present value for B is 1.95. So A is providing a higher value for this shorter project than B, even though B has a higher net present value. Now, another technique that we can use is something called the replacement chain. This technique assumes that projects are repeated until they have the same ending point. We then calculate the present values of the net present values. Again, we select the project with the largest sum net present value. This technique doesn't minimize the number of times the project is repeated. In this case, it multiplies the two lifespans and then repeats each project for that time frame. So in this example, it turns out right that we would do project A twice. That means we do it once, it ends in 2 years. We do it again, it ends in 2 years. That's 4 years. They would be equal. Where this gets a little bit strange is if those lifespans are not easily divisible with each other. You know, what if project A was 5 years and B was 8 years? Again, so this technique that I use here assumes we multiply these out. So it's going to be done, A would be done 4 times, ending in 8 years. B would be done 2 times, ending in 8 years. And that's this replacement chain. Another concern we should have is something called the difference between economic life and physical life. First, you have to consider operating the project for its entire profitable life. So the optimal economic life might be shorter than its actual physical life. It could last a long time, but it may not be as profitable in the future. So this process is going to allow us to minimize future expenses. As the assets get older, they start breaking down. Maybe they create more scrap and bad products. So we want to minimize that. So, for example, Intel often retires its semiconductor fabs. I'm not sure what fabs is, before the physical end of life because newer technology makes the older technology uncompetitive. This shows that the economic life is not just the physical life. So, how we do this is we need to estimate the salvage value at the end of each year. So, if we do this project, we spend $100,000. The very first year, we make $50,000 in cash flows, and we sell the project for $85,000. We end it in 1 year. The net present value of that time frame, 17,000, modified returns 35%, internal rate returns 35%, profitability is greater than 1. It's a good project. But as you see, if we continue down the line, you see that net present value is growing. And at 3 years, it's 37,000 now. At 4 years, it's 41,000. But if we did it for one more year, it would now have less value to the firm. So this abandonment value is a process where we can ultimately maximize the value of a project based on its economic life, not its physical life. So that's the end of our videos here on capital budgeting. Look forward to seeing you in the next video. Bye-bye.